Ohm's law. 1 microampere flowing in 1 ohm causes a 1 microvolt potential drop. Georg-Simon ohm. How voltage, current, and resistance relate. An electric circuit is formed when a conductive path is created to allow free electrons to continuously move. This continuous movement of free electrons through the conductors of a circuit is called a current, and it is often referred to in terms of flow, just like the flow of a liquid through a hollow pipe. The force motivating electrons to flow in a circuit is called voltage. Voltage is a specific measure of potential energy that is always relative between 2 points. When we speak of a certain amount of voltage being present in a circuit, we are referring to the measurement of how much potential energy exists to move electrons from one particular point in that circuit to another particular point. Without reference to 2 particular points, the term voltage has no meaning. Free electrons tend to move through conductors with some degree of friction or opposition to motion. This opposition to motion is more properly called resistance. The amount of current in a circuit depends on the amount of voltage available to motivate the electrons, and also the amount of resistance in the circuit to oppose electron flow. Just like voltage, resistance is a quantity relative between 2 points. For this reason, the quantities of voltage and resistance are often stated as being between or across 2 points in a circuit. To be able to make meaningful statements about these quantities in circuits, we need to be able to describe their quantities in the same way that we might quantify mass, temperature, volume, length, or any other kind of physical quantity. For mass, we might use the units of kilogram or gram. For temperature, we might use degrees Fahrenheit or degrees Celsius. Here are the standard units of measurement for electrical current, voltage, and resistance. The symbol given for each quantity is the standard alphabetical letter used to represent that quantity in an algebraic equation. Standardized letters like these are common in the disciplines of physics and engineering, and are internationally recognized. The unit abbreviation for each quantity represents the alphabetical symbol used as a shorthand notation for its particular unit of measurement. And, yes, that strange-looking horseshoe symbol is the capital Greek letter. Just a character in a foreign alphabet. Apologies to any Greek readers here. Each unit of measurement is named after a famous experimenter in electricity. The amp after the Frenchman André M. Ampere, the volt after the Italian Alessandro Volta, and ohm after the German Georg-Simon ohm. The mathematical symbol for each quantity is meaningful as well. The R for resistance and the V for voltage are both self-explanatory. Whereas I for current seems a bit weird, the I is thought to have been meant to represent intensity of electron flow, and the other symbol for voltage, E, stands for electromotive force. From what research I've been able to do, there seems to be some dispute over the meaning of I. The symbols E and V are interchangeable for the most part, although some texts reserve E to represent voltage across a source such as a battery or generator, and V to represent voltage across anything else. Ohm expressed his discovery in the form of a simple equation describing how voltage, current, and resistance interrelate. In this algebraic expression, voltage E is equal to current I multiplied by resistance R. Using algebra techniques, we can manipulate this equation into two variations, solving for I and for R, respectively. Let's see how these equations might work to help us analyze simple circuits. In the above circuit, there is only one source of voltage, the battery, on the left, and only one source of resistance to current, the lamp, on the right. This makes it very easy to apply Ohm's law. If we know the values of any two of the three quantities, voltage, current, and resistance in this circuit, we can use Ohm's law to determine the third. In this first example, we will calculate the amount of current I in a circuit. Given values of voltage E and resistance R, what is the amount of current I in this circuit? In this second example, we will calculate the amount of resistance R in a circuit. Given values of voltage E and current I, what is the amount of resistance R offered by the lamp? In the last example, we will calculate the amount of voltage supplied by a battery. Given values of current I and resistance R, what is the amount of voltage provided by the battery? Ohm's law is a very simple and useful tool for analyzing electric circuits. It is used so often in the study of electricity and electronics that it needs to be committed to memory by the serious student, for those who are not yet comfortable with algebra. There's a trick to remembering how to solve for any one quantity. Given the other two, first, arrange the letters E, I, and R in a triangle like this. If you know E and I, and wish to determine R, just eliminate R from the picture and see what's left. If you know E and R, and wish to determine I, eliminate I and see what's left. Lastly, if you know I and R, and wish to determine E, eliminate E and see what's left. Eventually, you'll have to be familiar with algebra to seriously study electricity and electronics. But this tip can make your first calculations a little easier to remember. If you are comfortable with algebra, all you need to do is commit here to memory. An analogy for Ohm's law. Ohm's law also makes intuitive sense if you apply it to the water and pipe analogy. If we have a water pump that exerts pressure voltage to push water around a circuit, we can model how the three variables interrelate. If the resistance to water flow stays the same and the pump pressure increases, the flow rate must also increase. If the pressure stays the same and the resistance increases, making it more difficult for the water to flow, then the flow rate must decrease. If the flow rate were to stay the same while the resistance to flow decreased, the required pressure from the pump would necessarily decrease. As odd as it may seem, the actual mathematical relationship between pressure, flow, and resistance is actually more complex for fluids like water than it is for electrons. If you pursue further studies in physics, you will discover this for yourself. Power in electric circuits. In addition to voltage and current, there is another measure of free electron activity in a circuit. Power. First, we need to understand just what power is before we analyze it in any circuits. Power is a measure of how much work can be performed in a given amount of time. Work is generally defined in terms of the lifting of a weight against the pull of gravity. The heavier the weight or the higher it is lifted, the more work has been done. Power is a measure of how rapidly a standard amount of work is done. Engine power is rated in a unit called horsepower, invented initially as a wafer steam engine. 1 horsepower is defined in British units as 550 ft-lbs of work per second of time. Speed of an engine's output shaft is measured in revolutions per minute, or RPM. Torque is the amount of twisting force produced by the engine, and it is usually measured in pound-feet, or lb/ft, not to be confused with foot-pounds. Neither speed nor torque alone is a measure of an engine's power. A 100 horsepower diesel tractor engine will turn relatively slowly, but provide great amounts of torque. A 100 horsepower motorcycle engine will turn very fast, but provide relatively little torque. Both will produce 100 horsepower, but at different speeds and different torques. The equation for shaft horsepower is simple. Notice how there are only two variable terms on the right-hand side of the equation, S and T. All the other terms on that side are constant too. Pi and 33,000 are all constant. The horsepower varies only with changes in speed and torque, nothing else. We can rewrite the equation to show this relationship. Calculating electric power. We've seen the formula for determining the power in an electric circuit by multiplying the voltage in volts by the current in amps. We arrive at an answer in watts. Let's apply this to a circuit example. In the above circuit, we know we have a battery voltage of 18 volts and a lamp resistance of 3. Using Ohm's law to determine current, we get. Now that we know the current, we can take that value and multiply it by the voltage to determine power. Answer: the lamp is dissipating, releasing 108 watts of power. Most likely in the form of both light and heat. Using algebra again to manipulate the formulae, we can take our original power formula and modify it for applications where we don't know both voltage and current. If we only know voltage E and resistance R, Using algebra again to manipulate the formulae, we can take our original power formula and modify it for applications where we don't know both voltage and current. If we only know voltage E and resistance R. Resistors. Special components called resistors are made for the express purpose of creating a precise quantity of resistance for insertion into a circuit. They are typically constructed of metal wire or carbon, and engineered to maintain a stable resistance value over a wide range of environmental conditions. Unlike lamps, they do not produce light, but they do produce heat as electric power is dissipated by them in a working circuit. Typically, though, the purpose of a resistor is not to produce usable heat, but simply to provide a precise quantity of electrical resistance. Resistor values in ohms are usually shown as an adjacent number. And if several resistors are present in a circuit, they will be labeled with a unique identifier number such as R1, R2, R3, etc. As you can see, resistor symbols can be shown either horizontally or vertically. Real resistors look nothing like the zigzag symbol. Instead, they look like small tubes or cylinders with two wires protruding for connection to a circuit. Here is a sampling of different kinds and sizes of resistors. Variable resistors must have some physical means of adjustment, either a rotating shaft or lever that can be moved to vary the amount of electrical resistance. Here is a photograph showing some devices called potentiometers, which can be used as variable resistors. For a practical illustration of resist's usefulness, examine the photograph below. It is a picture of a printed circuit board, or PCB, an assembly made of sandwich layers of insulating phenolic fiber board and conductive copper strips, into which components may be inserted and secured by a low-temperature welding process called soldering. The various components on this circuit board are identified by printed labels. Resistors are denoted by any label beginning with the letter R. Another circuit board example shows resistors packaged in even smaller units, called surface mount devices. This particular circuit board is the underside of a personal computer hard disk drive, and once again the resistors soldered onto it are designated with labels beginning with the letter R. There are over 100 surface mount resistors on this circuit board. And this count of course does not include the number of resistors internal to the black chips. These two photographs should convince anyone that resistors devices that merely oppose the flow of electrons are very important components in the realm of electronics. All we've been given here to start with is the battery voltage 10 volts and the circuit current 2 amps. We don't know the resistor's resistance in ohms or the power dissipated by it in watts, surveying an array of Ohm's law equations. We find two equations that give us answers for unknown quantities of voltage and current. Inserting the known quantities of voltage E and current I into these two equations, we can determine circuit resistance R and power dissipation P. For the circuit conditions of 10 volts and 2 amps, the resistor's resistance must be 5. If we were designing a circuit to operate at these values, we would have to specify a resistor with a minimum power rating of 20 watts, or else it would overheat and fail. For instance, our previous circuit example with the 3 ohm lamp, we calculated current through the circuit by dividing voltage by resistance IR with an 18-volt battery. Our circuit current was 6 amps. Doubling the battery voltage to 36 volts resulted in a doubled current of 12 amps. All of this makes sense, of course, so long as the lamp continues to provide exactly the same amount of friction resistance to the flow of electrons through it. 3 ohm. Circuit wiring. We've been analyzing single battery, single resistor circuits with no regard for the connecting wires between the components, so long as a complete circuit is formed. Does the wire length or circuit shape matter in our calculations? Let's look at a couple of circuit configurations and find it out. When we draw wires connecting points in a circuit, we usually assume those wires have negligible resistance. As such, they contribute no appreciable effect to the overall resistance of the circuit. And so the only resistance we have to contend with is the resistance in the components. Here, we only have 2 components excluding the wires, the battery and the resistor. Though the connecting wires take a convoluted path in forming a complete circuit, there are several electrically common points in the electron's path. Points 1, 2, and 3 are all common to each other because they're directly connected together by wire. The same goes for points 4, 5, and 6. The voltage between points 1 and 6 is 10 volts, coming straight from the battery. However, since points 5 and 4 are common to 6, and points 2 and 3 common to 1, that same 10 volts also exists between these other pairs of points. Polarity of voltage drops. As the current encounters the 5 ohm resistance, voltage is dropped across the resistor's ends. The polarity of this voltage drop is negative at point 4 with respect to positive at point 3. We can mark the polarity of the resistor's voltage drop with these negative and positive symbols in accordance with the direction of current. We could make our table of voltages a little more complete by marking the polarity of the voltage for each pair of points in this circuit.